students. Welcome to the next lecture of Environmental Modeling and Simulation. Today we are going to start the topic of dynamics. As the name suggests, dynamics is the study of things that change with time. So time here is our independent variable, and our interest typically is to find out other variables that depend upon time. So here we are dealing with quantitative problems, problems where we know certain variables are changing with the variable of time. And for example, if we take the two-body problem that was solved by Newton many centuries ago, in two-body problem, we are interested in finding the spatial location of two bodies along with their velocity and how it changes with time. The field of dynamics started when Newton solved the two-body problem, and he could generate two explicit equations for body number 1 and a similar equation for body number 2, telling us information on exact position, velocity at any given time of the two bodies. And once Newton solved the two-body problem, mathematicians across the world raced to solve the three-body problem. Now a three-body problem typically, for example, can be the exact position, velocity of three bodies, Sun, Earth and Moon at any given time. While we know the typical behavior to expect when Earth and Moon move around each other and around the Sun, it proved nearly impossible to solve the three-body problem. Why was three-body problem so hard? It turns out that when we are dealing with three bodies, each of them are exerting gravitational force on each other, pulling each other and still moving around each other. The equations that the scientists were trying to generate, the mathematicians were trying to generate, were dependent on each other. So let's say, for example, this is the explicit equation that we wanted for body number 1 and a similar equation for body number 2 and then another equation for body number 3. What mathematicians soon found out that these equations depended on each other, and it was nearly impossible to write explicit equations. And until the mathematics developed even further, the field of dynamics stopped here, being able to solve only two-body problems, but not being able to solve the three-body problem. And this continued until 1800s when Poincare found a very different approach to solve the three-body problem. Now, very important thing to note here that in this approach, the Newtonian approach, we are very interested in finding out the exact position, the exact momentum and at a given particular time of the bodies in question. Poincare suggested a very different approach, which is a qualitative approach. Now, how does qualitative approach differ from a typical quantitative approach? So far in your academic career, most likely you have only come across the quantitative approach, where we tell you, hey, this is the initial position, this is how the system is changing. For example, this is how the Earth is moving around the Sun. Can you find out the exact position and velocity of the Earth around the Sun in this particular direction at a given particular time? This is a typical example of a quantitative problem. In qualitative problem, I am not so much interested in precise position, precise velocity or precise values of the variables at any given time. I am more interested in an overall behavior. For example, the question in case of a qualitative approach might be, does the Earth collapse into the Sun given enough time? Or will the Earth move away from the Sun, escaping into infinity after some amount of time? Now that time can be very small or very big. But once we answer this qualitative problem, we know the general behavior of the system. So Poincare gave this revolutionary idea that it is not necessary to know the exact position or the exact values of the variables to understand a system. We can approach in a very different way, which is a geometric way, and understand how a system behaves, the qualitative approach. So today in our lecture, I am going to give you insights into a very different way of approaching our models and writing models, where instead of using the quantitative approach, we use qualitative approach. And I want to start by giving you an example of a typical quantitative model. So this is a first order decay model, and I am pretty sure that in your 11th, 12th or in your engineering, you have solved many problems that use a similar model. So let's say we have a radioactive material with initial mass m0, right? And it is decaying with first order. So we are having a situation where this mass decays after a given time, first order kinetics. So the unit of k would be per time. and at any given time the mass is empty. So we know that the rate at which the mass of the radioactive material will decay is given by this, the amount of mass at any given time. So this is your equation. By the way, this is exactly what dynamics is about, trying to explain the system, trying to find the values at any given time, trying to study how things change with time. So if you know this equation, which I have written here, you can find out that if m naught was the initial radioactive mass, after any given time, how much mass will be left. In this particular equation, this is a one-dimensional system, and when I say one-dimensional system, what I mean is, to understand the system, to know everything about the system, you need to know information about only one variable, and the variable here in the question is the mass of radioactive material. So in this one-dimensional system, if you know what was the initial mass at any given time, you can find out the leftover radioactive material. This is a quantitative approach. You know exactly how things are changing. A qualitative approach would ask a simple question: is more mass created over time? Do I end up with infinite amount of radioactive material, or do I end up with nothing after sufficient time has passed? So you see, in this particular case, since we know the equation, this is a linear problem, it's a very simple problem, and it's one-dimensional problem. We can very easily answer the qualitative questions just by looking at quantitative issues. Now let's look at a very different model. I'll give you a hint right away. This model is the model of a simple harmonic oscillator pendulum. So quantitatively, we all know how a pendulum behaves. So quantitatively, we know the pendulum behaves like this. The acceleration is equal to this. Now, if you look at this equation, it is something that you can very easily integrate and find an explicit answer to. However, if you did not know that this is the equation of a simple harmonic oscillator, it's very difficult to find out the behavior of the simple harmonic oscillator. On the other hand, if you know how a pendulum behaves, we can ask a very simple qualitative question: how does a pendulum behave? And anyone who does not even know this simple movement of how pendulum behaves can explain that, hey, a simple pendulum is a bob attached to a rope with a slight displacement. Now, the displacement here in question x can be small or large. We are not approximating, note, we are not approximating sin x is equal to x for sufficiently small x. If you do this approximation, this is a very easy problem to solve. But if you do not approximate, this is a very difficult problem to solve. In your 11th, 12th, when we taught you, or when your teachers taught you simple harmonic oscillation, a very simple assumption was made, which is x tends to 0. And when x tends to 0, sin x tends to x. So if you live with this assumption, you are making very small movements on either direction, either side of the pendulum. And in this case, it is very easy to integrate it and figure out the exact position and the momentum of the pendulum at any given time. So in this case, the quantitative approach does not fail you. However, what happens when the x is sufficiently large? What happens when the x is very large? When you make this assumption, you will not be able to predict how the pendulum is going to behave when the x is very large, when the initial displacement is very large. So this is where the qualitative approach comes. Intuitively, since we have all played with pendulum like toys in our childhood, or even whenever, doesn't matter, we know intuitively how a pendulum moves. Given that as long as the oscillations are relatively small, we expect the pendulum, the bob of the pendulum, to move to and fro around the central position, the velocity being least at the extreme position, highest at the original initial starting position when it's aligned with gravitational force. If the initial displacement is large enough, instead of oscillating to and fro, the pendulum will run in circles. This is a qualitative understanding of how a pendulum moves. When problems get really hard, for example, when x is not tending to 0, the simple harmonic oscillator is no longer a simple problem to integrate and find an explicit equation which may help or may not help you understand how pendulum moves. To understand how a pendulum works, a qualitative approach is very helpful, unless you need to find out, hey, for this initial displacement, this is the pendulum situation. At this particular time, what velocity, what position will I find the bob in? Unless you really need to find that information, a qualitative approach is perfect. And now I want to show you a very simple geometric approach to solve the qualitative questions. And we will start with a very simple model. And the model is of exponential growth. I'm sure during your undergraduate, during your perhaps even your 11th and 12th, you have studied exponential growth. Now, since I have a background in environmental microbiology, I'm going to take an example from environmental microbiology, which is binary fission of bacteria. The way bacteria grow, so let me write the model here. I'm going to write bacterial growth model because that's the example I'm giving you. Don't worry, even for environmental engineers, this is a very relevant model. And this particular model is exponential growth. Before we knew how bacteria grow, how could we predict the growth of bacteria? Before we knew that bacteria actually grow and split into daughter cells, we had information from our lab studies on how the bacterial numbers are changing. So what people noticed was, let's say we are starting with n number of initial bacteria, and there are different ways of measuring this, and I'm not going to go into that because this is the modeling course, not an environmental microbiology course. So let's say I'm starting with n amount of bacteria. The scientists observed that in lab, in pure cultures, after some given time t, the number of bacteria doubled. After another given time t, the number of bacteria again doubled. So after n t had passed, now you can estimate the number of bacteria here. 2 to the power small n, n here, the capital N here is the initial microbial population, initial bacterial population. So even before we knew about binary fission, we knew that the bacteria are doubling after a given time, and we knew that this time t here, actually I should have written tau, is fixed for a particular bacterial strain, a bacterial species, and it varies for different kinds of bacteria. So once the scientists knew this, how the bacteria behave, they were able to plot the number of cells, bacterial cells with time, and what they found was that if this is, let's say, n naught, the initial number, the growth looks like an exponential curve. Now, if you remember from the first lecture, sometimes it is the observations that help us write our model. So this is a typical example where the observations inform your model, and then the model help you explain the observation. And I'll be returning to this particular approach to modeling throughout the course. So once the scientists had information on how the bacterial count is changing with time, the next step was to model it. So to model it, what we figured out was how number of bacteria is changing with time, and we figured out that dn by dt here is equal to some constant, let's put it k, and number of bacteria. Now this works when the t is sufficiently small, not very large, and this works only for very simple microbes which divide by binary fission. For certain microbes that are not bacteria, non-bacterial microbes like eukaryotes, this model would not work. So this is a very simple model where you can solve it quantitatively, get an explicit equation. This is not hard. You can get an explicit equation, and for any given time, any initial number of bacteria, you can find out precisely the number of bacteria you expect in your culture. How will you solve this with geometric approach? That's the question. So let's move on. We are going to find a very different way of looking at the same model. So let's say we have our model. Now from our lab observations, we have figured out that this is how our bacteria seem to grow. In geometric approach, we are not going to integrate. In geometric approach, we are going to draw phase portraits. So if you look at this system, you need to know only one thing to understand everything you need to know about this system, which is the number of bacteria right now. K is a constant, so you will know the K. If you know the current population of bacteria, you can predict the exact amount of bacteria at any given time in past or in future. So in geometric approach, what we are going to do is, since this is a one-dimensional model, we need information only about one variable to understand the system. We are going to draw a graph, a two-dimensional graph, not a one-dimensional graph, where we are going to put our dimension here, n, in x-axis and the rate at which n is changing in y-axis. Now, this graph in geometric approach is referred to as a phase portrait, and I will tell you what phase portrait is in a bit. Now, if you plot dn by dt with time, this is do not confuse this for this graph where you are plotting number of bacteria with time and you are getting an exponential curve. This is a different curve. You are plotting dn by dt versus n. Now, notice this is a straight line and this line passes through 0. So, this is how your line looks like. Now, notice one thing, when n is less than 0, dn by dt is negative. But in this particular case, since we are dealing with living organisms which are bacteria, n can never be less than 0. So, our situation means we can ignore the left side of the y-axis. So, this is our graph here. So, once we have this, now think about it. Let us say our starting position is here. At time equal to 0, we are starting with this number n naught. Okay? Now, notice here, it is a qualitative approach, so we are not going to do any calculations. Look at this graph. At n naught, dn by dt is positive, right? It is above the x-axis, which means the number of bacteria is going to grow, which means if the bacterial population is here at time t equal to 0, as time progresses, it is going to move in the right direction. So, at n equal to t, we will be somewhere here. Where we will exactly be, we do not know. This is not quantitative approach, but we know that as time progresses, the number of bacteria will increase. Now, we know that as time progresses, this will increase if we start from here. What happens if we are starting from n naught is equal to 0? If you are starting from n naught equal to 0, look at the value of dn by dt here when n naught is equal to 0, it is 0. So, dn by dt is equal to 0, which means no change in the number of bacteria. So, if you are starting with no bacteria, you end up, no matter how much time progresses, you do not change, you stay here, there is no growth. So, in this very simple example, by geometric approach, we already know that in exponential growth, if we are starting with 0 bacteria, we end up with 0 bacteria. There is no spontaneous generation of bacteria. However, if you are starting with any number of bacteria which is greater than 0, the number of bacteria continue and keep on increasing. Now, the question is, what happens if we wait for infinite amount of time or sufficient time? So, let us make this x-axis longer to understand what happens when time tends to infinity. So, you notice here that as some finite amount of time passes, n increases, and as n increases, dn by dt remains positive. But notice something else. When n at time t equal to 0 was n naught, this was the magnitude of your dn by dt. Remember, dn by dt is the velocity, the rate at which n is changing. After finite amount of time passed, this is your value of bacteria nt, and if you draw a vertical line, you will see that dn by dt, the magnitude of dn by dt velocity has increased. So, from here you have gone here. So, basically as time passes and the number of bacteria continue to increase, the rate, the velocity at which n is changing also increases. So, we can understand qualitatively that as time passes, the number of bacteria will increase rapidly, more rapidly than it did before. So, let us say after sufficient, a big amount of time has passed, n capital T, you again put a vertical line up and you see that dn by dt has increased even more. So, the rate, the velocity at which n will change is much higher here than it was here, than it was here. So, now let us plot, let us try to understand the result of our qualitative approach. So, now with this, without calculating, without integrating anything, we already know that if I want to understand how n is changing with time, this graph, let us say I am starting with n naught. dn by dt is positive, so things are going to go up, the value is going to increase. After t time has passed, the small t, dn by dt has increased. So, let us say here the time is 0, here the time is small t. Now, here the rate at which n is changing is faster, which means the slope of this line would be more steep. So, I am expecting here things to change at this velocity with this slope. Similarly, once I reach this time, let us say capital T, dn by dt is even higher than it was at the case of small letter t. So, here I am expecting even a more steeper slope. So, even without integrating, without solving the equation, we know that the behavior tends to move like this. This is qualitative approach, a very simple example. Now, if you look at this, there are certain limitations in this model. The first limitation in this model is that according to this model, the bacterial population will continue to increase ever so rapidly. And very soon, the mass of the bacteria in the petri dish will exceed the original mass of the earth, which is not something we have observed. So, can you take a moment here, pause the video and think about why is this model that works so well for bacterial growth? Why does this model has such a big limitation? Because according to this model, the bacteria never stop growing and they are always doubling after each fixed t time that they pass through. Okay, students, I hope you have some idea about why this is happening. And if not, let me share with you the reason why bacteria don't grow indefinitely and do not attain a mass in a lab that is greater than the mass of the earth to begin with is because they run out of resources. Once sufficient population has reached, once the bacteria are a particular population, let us say k, n is equal to k, the resources become limited. So, the bacteria are no longer able to multiply so efficiently, they are no longer able to double after every doubling time, and the rate at which they grow slows down. So, what we observe in the lab actually looks like this. Initially, yes, the growth looks exponential, and then it starts slowing down, and then it starts slowing down further. Once the bacterial population approaches a particular value, it almost stops growing. So, instead of seeing a shooting up exponential growth, what we see is more of a gentle S growth, and this is the second model that we will study. So, now we look at another model of bacterial growth that makes more sense for the observation that I shared earlier, which is the bacteria don't grow indefinitely in the lab or in the petri dish. So, this model is known as logistic model, again a model that most likely you have come across. But instead of solving this model quantitatively, which is by integrating it, we are going to solve it qualitatively. So, if you remember from your undergrad classes and from perhaps your 11th and 12th, the logistic model looks like this. Let us say somebody gives me this model. I can integrate it because this model can be easily integrated, and I can find an explicit equation for n is equal to something function of time, right? But that will not help me understand how this model is behaving. On the contrast, the qualitative model will really help me understand how this model is behaving. Remember, this is still a first one-dimensional model. Why is it a one-dimensional model? Because to understand everything I need to know about the system, all I need to know is at a given time how many bacteria are present. If I know that, I can find out the number of bacteria at any given time in past or in future. So, in this model, how will you apply the geometric approach? Similarly, like we did in the exponential model, since this is a one-dimensional model, we are going to make a 2D graph. On x-axis, we are going to plot n, which is the information we need. On y-axis, we are going to plot dn by dt, which is the velocity. Now, if you draw this plot, it will look something like this. And this position is k, this is 0. Now, you may ask me, how do I know if I am not going to solve this, how do I know how to plot it? So, I am going to make this very easy for you. How do you plot a graph without putting in information? So, here is n, here is dn by dt. Pay attention here, students, this is very important. The first thing we want to do is find the zeros. So, zeros are when your velocity, your rate at which things are changing is 0. That is when your curve that you are going to plot on this is going to intersect with x-axis. So, in this case, what I want you to do is make dn by dt equal to 0. So, now you have n 1 minus n by k is equal to 0. When will this be the case? This will be the case when either n is 0 or when n is equal to k. So, I know that at n equal to 0 and at n equal to k, this graph intersects the x-axis. This plot intersects the x-axis. Now, the other information I need to know is on the left side of this first 0, between the two zeros, and on the right side of the second 0, what are the sign of this curve? So, I can do one thing, I can take a value that is either less than the first 0. So, I can take a negative value like -1, -k, -2, or a value between 0 and k, or a value greater than k, and find the sign of this. So, all you need to do is, if you, let us say the k is 10. So, you just need to put a value between 0 and 10 and find out what is the sign of dn by dt. Now, I am not going to do it here, but if you do this, you will notice that when n is less than 0, dn by dt is less than 0. When n is between 0 and k, dn by dt is greater than 0. And when n is greater than k, dn by dt is less than 0 again. In this particular system, because it is a very simple system, you only need to find one of these, not all three. So, let us say when n is less than 0, dn by dt is less than 0, you figure it out, you put a negative value instead of n, and you know this is negative, and depending on this, this is going to be positive, depending on the value of n. Well, it does not depend upon the value of n, this is going to be positive. How? Here n is negative, you know that. Here n is negative, which means n by k is negative, which means minus n by k is positive, which means 1 minus n by k is also positive. So, we are multiplying a negative term with a positive term. Let me clean this up for you. So, we are multiplying a negative term with a positive term. We are going to get dn by dt is less than 0 when n is less than 0. So, we know this for sure that on the left side of the first 0, your curve is like this. Notice why I have intersected the curve at 0? Because 0 is a 0. Now, what is going to happen is, since here also the curve has to intersect, there is no other way for this curve to behave but like this. So, even without solving, I know this is how the plot looks, and once you get experience, you can do this within half a minute. In the next lecture, we are actually going to interpret this using the geometric approach and understand how logistic model behaves. Thank you, and see you again in the next lecture.